everyone, my name is Isabel Delgado. I'm a master's student in mechanical engineering at Florida Institute of Technology. And today I'm going to talk about the mechanical characterization of calcification in diseased coronary artery with atomic force microscopy. First, why did we do this? The CDC assured that the leading cause of death in the United States is heart disease, and in order to decrease these statistics, the calcium scoring has been used as a risk stratification for cardiovascular diseases. Before, we used to think that these diseases were degenerative and due to aging, but now we know that it could be the complication of several others like diabetes, hypertension, obesity, and so on. Here we can note the plaque formation and the effects. As the disease progresses, the lumen area of the artery becomes smaller, and also the arterial elasticity decreases, making it harder for the artery to fulfill its main functions. And the fatal result is a fracture of the tissue, which can lead to lethal consequences. The main purpose of this research is to study the mechanical properties of the calcification in order to provide insight on its mechanical behavior for better treatments of cardiovascular diseases. How do we do this? First, we harvest the cadaver artery and divide it into two sections. The first one was heavily calcified, as the one we can note here, and the second one was a more cleaner region where we call healthy artery. Then we proceed with the cross-sectioning, where we use cross-section of 5 micrometer thickness. For the staining, we use Alizarin Red to locate the calcification and also to assure that the group we called healthy artery was in fact free of calcium. Later, with the atomic force microscopy, we choose a spherical tip of 5 micrometer, and the artery was totally submerged in 30 millimeters of PBS. We decided a scanning area of 10 by 10 micrometer and have 2 locations per artery. That resulted in a 64 force curves. For our staining results, here we can see that under the AFM optics, the calcification just seems like a darker spots. So what we did was to compare the AFM image with the staining results. That way we can assure that the area that we were testing was in fact calcification. Also, we can see the difference between the healthy artery and the calcified artery. The healthy artery, we see no red spot, meaning that it's free of calcium. But we can see a thickening in the arterial wall, and this is because the artery itself was affected by the disease, but there is no calcification in this group. However, here we can note the plaque, and also we can see the heterogeneity of the calcification. Since we can see different levels of red intensity, we can see lighter spots and darker spots, which means the difference in the accumulation of calcium. Later on, for our stiffness results, here we have a sample curve of force displacement obtained with the AFM test, and in order to find the Young's modulus of the material of each location, we fit it with the Hertz model. The result of the stiffness assure that the calcified artery has a significant difference between the healthy artery, but we can also note the heterogeneity of the artery, as different location provided different stiffness results. However, we can see that the calcified region has a significant difference with the healthy artery. The main purpose of this research was to provide insight in the mechanical properties of calcification for better vascular therapies. Thank you for your attention.